Hello everyone. Today we'll study about terms and term symbols. Suppose your teacher asks you to write the electronic configuration of carbon. How will you proceed? First, you will write down the atomic number of carbon, that is 6, which means there are 6 electrons in carbon. Now, you will distribute these 6 electrons into different orbitals. But to do this, you have to consider certain rules. Opco principle, Hund's rule, Pauli's distribution principle, etc. Now, after obeying all these rules, you will write the electronic configuration of carbon as 1s2, 2s2, 2p2. But see here, there are 2 electrons in the p orbital. Won't they repel each other? They will. There are 2 electrons in s orbital as well. These electrons will also repel each other. Which means, when we write the electronic configuration, we are not considering the repulsion between electrons. Thus, a configuration is the arrangement of a given number of electrons into certain sets of orbitals without considering the interactions between them. Now, there are 3 p orbitals, px, py and pa. From this configuration, we will not be able to understand to which of these orbitals these 2 electrons belong. Thus, the configuration does not tell which of the degenerate orbitals is occupied and which is not. Now, if we consider the interelectronic repulsion between the electrons in a configuration, each of the energy levels in a configuration will split again to give a number of energy levels. We call this as terms. So, term is an energy level or a set of degenerate energy levels resulting from the interelectronic repulsion of a configuration of a free atom or ion. All the energy levels of an energy term are degenerate. But the interelectronic repulsions for all the configurations and all the electronic arrangements of a configuration may not be the same, which means there can be several energy terms in a configuration. Also note that a term corresponds to a set of microstates. You will understand this from our later discussions. Thus, a term is an energy level of an atomic system specified by an electronic configuration which arises due to interelectronic perturbations. Terms with different L values denote different energies. Consider a state with a given L value and a given S value. It consists of a group of components having energies that are close to each other, and the number of components of the group is equal to the number of possible J values, which we call as multiplicity. Multiplicity is given by the formula 2s plus 1, where s represents the total spin angle, spin quantum number. For a given value of L, let the s value be equal to half. What are the J values possible? J can have values ranging from L plus S up to L minus S. Let's substitute the value of S here. So J is equal to L plus half, L plus half minus 1, etc. up to L minus half. The first value is L plus half. Second value is L plus half minus 1, that is L minus half. L minus half is already written here. You can take one J value only once. So there are only 2 possible J values, that is L plus half and L minus half. Let's see whether it is true by checking it with the formula. That is, multiplicity is 2s plus 1, that is 2 into half plus 1 is 2. Now since multiplicity is 2, we call it as a doublet. Now for a given value of L, let s equals 1. Then let's see how many J values are possible. J is equal to L plus 1 up to L minus 1, that is L plus 1. L plus 1 minus 1 is L itself, then L minus 1. So J can have 3 values. Multiplicity formula also gives you same value of 3, and we call it as a triplet. Now consider single s electron outside a closed shell, means an electron in an s orbital, say for example in a configuration like 4d10 5s1. Here L value, small l value for s electron is 0 and s value is half. Now capital L value will be summation of L, that is 0 itself. Capital S value is also summation of S, that is half itself. What are the possible J values? J is equal to 0 plus half up to 0 minus half. 0 plus half is half, 0 minus half is minus half. We will not consider negative values of J. So J can have only one value here, that is half. Now let's see whether the multiplicity formula will also give it the same value. Multiplicity is 2s plus 1, that is 2 into half plus 1, that is 2. So you will get a tablet here. Now which is correct? Note that multiplicity is equal to 2s plus 1 only if L is greater than s. If L value is less than s, then there is only one possible value of J, even though 2s plus 1 is greater than 20. So all such information pertaining to a system of electrons is conveyed by a single symbol called a term symbol. The term symbol indicates the various terms that can exist for a particular configuration. A term symbol is written as 2s plus 1 Lj. 2s plus 1 is a superscript on the left hand side and J is a subscript on the right hand side. J represents the resultant angular momentum of the number. S represents the total spin of electrons and 2s plus 1 represents the spin multiplicity, which gives the number of orientations of S in space. Now L represents the term letter according to the value of L. That is, we are not writing the value of L here, but we will be writing a term letter corresponding to the value of L. And this represents number of d-site orbital energy levels contained in it, which means the orbital degeneracy is given by the formula 2l plus 1. Say for example, if L equals 2, then orbital degeneracy will be 5. If L equals 1, then orbital degeneracy will be equal to 3. Now this table will give you the term letter corresponding to the different L values. If L equals 0, the term letter is S. If L equals 1, the term letter is P. For 2, it is T. For 3, it is F. Now for L equals 4, you will continue in the alphabetical order from F. That is, next letter in the alphabetical order is G. For 5, it is H. For 6, it is I. For 7, it should have been J, but we are writing K here. It is already used for representing the total momentum. So instead of J, we will write the next letter in the alphabet, that is K. Then you will continue as K, L, M, etc. Now term is characterized by a particular value of L and a particular value of S, as we have already seen. Now there are 12 plus 1 values at hand, which means the orbital degeneracy will be equal to 2l plus 1 and spin degeneracy or spin multiplicity will be 2s plus 1. The total degeneracy or multiplicity of a term is the product of these two values, that is 2l plus 1 into 2s plus 1, and this represents the total number of energy levels possible in a term. Now let's consider the terms for a Dn system. First we'll see a D1 system. Since it is d electron, the L value is 2 and the total L value will be summation of L, that is 2 itself. For S value, it is half. Capital S is summation of S, that is half itself. Multiplicity is 2 into capital S plus 1, that is 2 into half plus 1, that is 2. Which means you can expect 2 J values. So J is equal to L plus S up to L minus S, that is 2 plus half up to 2 minus half. 2 plus half is 5 by 2. 2 minus half is 3. Now let's write the term symbol. 2s plus 1 Lj. L value is 2 and the corresponding term, that is d. Multiplicity is 2. So the terms are 2d. J value is 5 by 2. So we write as 2d 5 by 2. The second value will be 2d 3 by 2. So see, there are two term symbols for this D1 system, but only one term, that is 2d, for D1 system. So there is only one term here, but there are two term symbols because there are two j values. For a D2 system, since there are two electrons, we will write L1 equals to L2 equals to. For the first electron, the L value is 2. For the second electron also, L value is 2. So total L will be L1 plus L2 up to L1 minus L2. That is 2 plus 2 up to 2 minus 2. You can have 5 values for L. And for each of these 5 L values, you have a term letter. For L value 4, the term letter is G. For L equals 3, the term letter is F. For 2, it is D. For 1, it is P. For 0, it is S. Which means for a D2 system, we have 5 different terms that are possible. Now, for the first electron, S is half. For the second electron also, S is half. So total S will be S1 plus S2 up to S1 minus S2. That is half plus half up to half minus half. That is 1 and 0. Now if S equals 1, then multiplicity will be 2S plus 1, that is 3. If S equals 0, then multiplicity will be 1. So, the different terms possible for D2 system are multiplicity 3G, 3F, 3D, 3P, 3S. Similarly, if multiplicity is 1, then 1G, 1F, 1D, 1P, 1S. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different terms are possible for D2 system. And for each of these terms, different j values are possible because j value is given by the formula L plus S up to L minus S. So we are not writing this because it is much complicated. Now, there are 10 terms possible. How will you find out which is the ground state or the ground term for the system? Or how will you arrange these terms in the increasing or decreasing order of energy? We will see that in the next module.